Start our lab lecture recording. So today we'll be looking at experiment 11C, steam distillation and the isolation of cinnamaldehyde. Cinnamaldehyde, as shown in the structure here, is the principal sort of aromatic component of cinnamon. It's often responsible for the characteristic smell of cinnamon. And in order to isolate cinnamaldehyde in its pure form, we're going to be isolating cinnamaldehyde via steam distillation. And the principal use of steam distillation is to isolate high boiling compounds that are immiscible with water that also don't form azeotropes. So this is mainly useful for isolating nonpolar or water insoluble components of natural product mixtures or reaction mixtures. So in this case, we have our cinnamon, and we're going to heat the cinnamon or place the cinnamon in boiling water or a source of steam. Now, to talk a little bit about the main distinction between steam distillation and simple distillation, it's important to highlight this key sentence here. Steam distillation deals with isolating high boiling compounds that are immiscible with water. Now, in simple distillation, as we talked about in 112, if we have hexanes and toluenes, they will mix and we'll get a miscible reaction mixture or miscible solution mixture, right? As a result, when the liquid phase partitions and establishes an equilibrium with the vapor phase, the composition of the vapor that we generate and the total vapor pressure will be a function of the pure vapor pressure as well as the mole fraction of each component in the mixture. This is classic Raoult's law, classic distillation theory from 112, right? This only applies because our two reaction components are miscible in the liquid phase. So we can generate these vapor-liquid composition curves, and as our liquid boils, we generate a vapor, and the composition of the vapor is different from the liquid phase. And the composition of the vapor depends on the mole fraction and the vapor pressure. So we can distill over and collect our distillate from our vapor. And as we notice, with each distillation, we're enriching our distillate in one component. The same way through multiple distillations, we're able to enrich our distillate in either hexanes or toluene. Does that idea make sense? Does that idea make sense? When the two mixture components are miscible, the vapor phase composition depends on the vapor pressure and the mole fraction of each component in solution. Now, in steam distillation, this is what's pretty cool about it. Water and your desired natural product extract are not miscible. So the vapor pressure exerted by this heterogeneous mixture will be based on the individual vapor pressures of water and your other extract components, such as cinnamaldehyde, that are immiscible with water. Now, we know that when this total vapor pressure matches the atmospheric pressure, the mixture will boil. Now, as a consequence of this, substituting these two expressions, we know that when this mixture is boiling, the atmospheric pressure will match the vapor pressure exerted by water and the vapor pressure exerted by cinnamaldehyde, which is our immiscible component. So, as a consequence of this idea that our two components are immiscible, water and in this case cinnamaldehyde each exert a vapor pressure, when the total vapor pressure of each component matches the atmospheric pressure, the mixture is boiling. And The boiling point for this mixture, the temperature at which the total pressure of each component matches the external atmospheric pressure, the boiling point inherently will be less than that of pure water for the mixture, right? Because for pure water boils when the atmospheric pressure matches the vapor pressure of water, right? And because we have this other component exerting a vapor pressure, inherently a lower temperature is required to reach the boiling point. Does this sound familiar from 102? Does that idea make sense? Because we have two components contributing a vapor pressure, inherently the boiling point will be at a lower temperature for this mixture than pure water. So if we have our water and cinnamaldehyde mixture, which is a heterogeneous mixture, water and cinnamaldehyde will each partition into the vapor phase, and the composition of our vapor phase and the total pressure exerted by this combined vapor phase will be based on the vapor pressure of each component at that temperature. So what this method allows us to do is it allows us to distill over this second component. It allows us to distill over cinnamaldehyde at a temperature less than the boiling point of water. So if we have our water cinnamaldehyde mixture and we heat it until it begins to boil, it will boil at less than 100 degrees Celsius, less than the normal boiling point, or less than the normal boiling point of water, pure water. This allows us to collect a mixture of water and cinnamaldehyde. And the real beauty of this method is that cinnamaldehyde naturally has a boiling point of around 200, and it allows us to distill over cinnamaldehyde as a mixture with water at a substantially lower temperature. And this only works because cinnamaldehyde and water are immiscible in the liquid phase. So, steam distillation allows distillation of high boiling compounds at low temperatures, and it avoids distillation at higher temperatures where compounds can decompose at their normal boiling point. If you try to distill cinnamaldehyde directly by just taking cinnamon and heating it to 200 degrees Celsius, you would notice decomposition of your cinnamaldehyde. So steam distillation is incredibly useful to isolate natural products that decompose at their boiling point. Does this theory make sense to everyone? Does everyone see how steam distillation works and when it is applicable? Any questions? Now, your isolated distillate is usually heavily enriched in the high boiling component by mass, because even though the vapor pressure exerted by cinnamaldehyde is going to be relatively low, it has a substantially higher molar mass than water. So your water cinnamaldehyde mixture that you collect from this distillation will have a fairly large mass of cinnamaldehyde as mass percent. Now, of course, we can't just drive off the water by heating the water for obvious reasons. We'll just end up repeating the steam distillation. So instead, we'll isolate our organic component via extraction with dichloromethane. From there, we'll collect the cinnamaldehyde enriched organic layers and concentrate our organic layers to yield pure liquid cinnamaldehyde. From there, we're going to record the mass of cinnamaldehyde, and by taking the ratio of the mass of cinnamaldehyde over the mass of raw material, the mass of cinnamon used, we'll be able to calculate and estimate the mass percentage of cinnamaldehyde in cinnamon. From here, we'll take a proton NMR and infrared spectra. The infrared will be collected in liquid film, not neutral. Because it's a liquid, you can load the cinnamaldehyde directly onto the IR probe crystal and it allows you to get a pretty reasonable IR spectra. Now, if we wanted to characterize cinnamaldehyde, can we take a boiling point? Would it be a reasonable technique in this lab to take a boiling point of cinnamaldehyde, considering all that we've discussed? No. And why? It will decompose. Exactly right. That's the entire reason why we did steam distillation. If we wanted to, there's another method of distillation that would also allow us to circumvent this decomposition issue. That's something to think about for your discussion. Anyway, so to characterize cinnamaldehyde, as with most unstable aldehydes and ketones or liquid aldehydes and ketones, instead, we're going to prepare the semi-carbazole derivative and measure the melting point of that derivative. So in this case, we're going to react cinnamaldehyde with this hydrazine derivative, semi-carbazole hydrochloride, and we'll form the imine product. Just like any other imine formation mechanism under acidic conditions, we're going to protonate the aldehyde carbonyl. Our nucleophilic amine will attack the carbonyl carbon. We're going to see a series of proton transfers to activate water as our leaving group. We're going to kick out water as our leaving group, and then we're going to deprotonate our nitrogen atom to give us the neutral semi-carbazole derivative. And once we have this neutral semi-carbazole derivative, we're going to measure the melting point of this derivative and compare our observed melting point for this derivative to the literature value mentioned in your lab manual. So that is a complete overview of this laboratory. Any questions that I can address? The literature mass percent, it's not fixed. It varies depending on the brand of cinnamon and the type of cinnamon. You shouldn't get a particularly large number for the mass percent, that's for sure. You don't have to report a literature mass percent, but you do have to report the mass percentage based on your experimental data. I'd say it's around 1 to 10%. So, any questions, any follow-up questions on this lab before we archive today's recording? Okay, so let's archive this recording.